Hello guys, I'll be solving this problem, which is count partition with max mean difference at most k. Okay, so the problem states that we have been given an integer array nums and an integer k. Okay, and our task is to partition nums into one or more non-empty contiguous segments, such that in each segment the difference between maximum and minimum is at most k. Okay, now, and finally we just need to return the total number of ways we can partition nums under this condition. Okay, and this number can be a big number, so due to that we'll be like moduling with 10 to the power 9 plus 7. Okay, cool. So if I draw out this problem, okay, so let's say I have some, okay, yeah, let's say I have some elements, let's say a0, a1, a2, a3, and up to, let's say, an. Okay, so here I have n minus 1 partition lines, right? Like this. Okay, so uh, if I simply think of a brute force, so what I can be doing, okay, so let's say for each partitions, okay, I divided it into segments. Okay, let's say I take one set of partition. Okay, so let's say I take like a0 to, let's say, some ap1 partition. Okay, and then the next segment will be starting with ap1 plus 1 up to, let's say, some ap2 partition. Okay, and like that, let's say there are some k partitions if I'm doing, so this will be some apk up to an. Okay, so when we are partitioning our arrays, we are basically like dividing into segments, right? So these are my segments. Okay, so a naive way is to like once you have this partition, okay, you can recursively get all your segments. Now in each of this segment, you just check whether your condition is satisfying. Okay, now the condition is basically the difference between the maximum and the minimum is at most k. So I'll be doing max of each segment. Okay, so for each of the segment, okay, I need to check this condition, and minimum of this segment should be less than equal to k. Okay, so if all of them are satisfied, I can like increment my answer. Okay, something like this. Cool. So if we go via this approach, okay, so I have n minus 1 partition lines, right? Which means if I code it recursively, okay, so it will be again a pick or not pick kind of a problem, right? So with that, I'll be doing like maybe around 2 to the power n minus 1 partitions. Okay, which is like very big, right? And as I look at the conditions here, so my number of elements can vary between 2 to 5 to the 5 times 10 to the power 4, right? So this will be a huge number of operations, right? Cool. So can we do something better? Okay, so let's look at a partition. Okay, so let's say if I have an array like this. Okay, let's say I denote my last element, okay, as, let's say, r. Okay, now let's assume that I have somehow partitioned my array. Okay, and for this r there exists a l. Okay, such that in this segment, okay, this condition is satisfying. Okay, now let's say for this guy, which is l minus 1. Okay, so for 0 to l minus 1 number of elements, okay, or like here basically like l elements. Okay, I know the count. Okay, in how many number of ways I can like maybe partition this many elements, okay, with them. Okay, so right now I haven't said like how can you do it. Let's assume that I know the count of it. Let's say m is the count. Okay, the number of ways, okay, to partition my let's say first l elements. Okay, first l elements. Okay, so if I have this count, and let's say for this segment, okay, this guy is also satisfying my condition. Okay, which basically means for this index, okay, I can say for my rth index, okay, it will be basically the number of ways I can partition this, right, which will be m. Okay, now let's say I have another guy, let's call it L1, okay, and for this is M1, okay, this will be L1 elements, okay. Let's say I have another guy, okay, for R, let's call it L2, okay. Now this segment is also satisfying my this condition, okay, which is like the question condition, okay, which means the number of ways, okay, I can partition this many elements, okay, those can simply take this new partition, right, and they will all be valid, right. Let's call this like M2 number of ways I can partition the first L2 elements, okay. So for this guy I can say, okay, I have a L1 and an L2, okay, and when I'm using L1, okay, there is like M1 number of ways I can do the partitions, okay, and for this when I choose L2 there are M2 number of ways I can do the partitions, okay. So I can see a relationship here, right. So that relationship will be, so the answer that I'm getting, okay, for my, let's say, R, okay, that is basically the somehow the summation of all the answer, okay, that I'm getting from L minus 1 index, okay, where L will vary between 0 to R, okay, and such that my L to R, okay, L to R is satisfying my question condition, okay, let's call it condition, okay, which is basically like max of, or let's write it properly, so max of L to R, okay, minus minimum of L to R, okay, that is less than K, okay. So for every index R, if I know like before that R, okay, I have this L1, L2, maybe L3 or maybe some LK, okay. So if I know the number of ways to partition the first L elements, okay, so their answer will basically get accumulated for my R, right. So this will be, yeah, okay. So you can see like we are somehow kind of using a DP, right, okay. So I can simply write like, if I know the number of ways, okay, for R, okay, that is basically the summation of all the valid L's, okay, valid L's between 0 to R, okay, and I'll be doing summation of dp of L minus 1, okay, cool. So with this we can like implement a dp kind of a solution, okay. So before doing that, let's define what exactly does this mean, okay. What is the state definition, okay. So the state definition, I can simply say that the number of ways, okay, to partition, okay, or to correctly partition my first R elements, okay. So if I have this answer stored in my DP, I can use those answer to calculate future values, right. So this is, oopsie. So yeah, this is my DP relationship, okay, cool. So with this we can implement a DP solution. So how it will look is, so if I'm saying if so my state definition is this, like, so the number of ways to correctly partition my first R elements, okay. So I can initialize my DP something like this, or let's say n be the number of elements in array, okay. I'll be creating a DP of n plus 1 elements, okay, because I need to consider the case where there are no elements, right. So I'll be initializing everything to 0. Okay, then I need to set some base condition here, right? So that's how we solve DP kind of a problem, right? So the base condition here will be DP of 0 equal to 1. Okay, how this is the base condition? So let's consider I have a array which has only one element. Okay, so let's say if I have only one element, let's say 100 is the array. Okay, so as per this condition, okay, my DP of if I form my DP array, okay, so it will look something like this, right? 0 1, okay, where the DP1 index will be designating my array's 0th index, right? So if so we can say like for this one element array, okay, there is one way to partition it, which is basically like the array itself, right? So if I want to compute the answer for this, okay, I need to set my DP of 0 as 1. Then only when I'm doing like when I'm trying to find DP of 1, I'll be adding up my DP of 0 there, right? Now if DP of 0 is 1, so that will give me my DP of 1, like a plus 1 here, right? So, or you can think of, let's say the whole array is a valid segment. Okay, so if my whole array is a valid segment, okay, then in order to take that into account, I need some kind of a null index, right? Okay, so that null index will symbolize my DP of 0 state. Okay, and that needs to be initialized with 1. Okay, so that when I'm at this index and I'm calculating like how many number of ways I can partition, okay, so this null index will help me, okay, to capture this array as a whole as a contribution to my answer, right? So yeah, that's why I'll be initializing DP of 0 as 1. Okay, then what I can do is, so I can simply write a for loop. Okay, so I'll be writing a for loop for r, I'll be starting from 1 to n, okay, inclusive, because my DP as per my DP condition, like I'll be using one base indexing, right? Then I'll be iterating over all possible else. So basically when I'm starting with a rth index element, okay, I'll be basically looking back, okay, so such that I will get this valid condition. Okay, so basically what I'm saying is, so I'll be using another variable or another iterator L, okay, that will start from r and it will go to 1. Okay, so for every index I'm going back, okay, and as I'm going back I'll be checking the condition of max minus min should be less than equal to k. Okay, so in order to do that, I can initialize my max as let's say nums of r minus 1, because this is one base indexing. Okay, or instead of nums I can switch to array. Okay, and I will be initializing mean. Okay, so this is basically kind of a window, right? Yeah, so when I'm starting with starting with r, I'm initializing my max and mean as array of r minus 1, array of like array of r minus 1, right? Now when I'm going back, okay, so I'll be first updating my max. This will be my max of what, this max nums of r minus 1, sorry, this will be L minus 1. Okay, and minimum will be mean of nums of L minus 1. Okay, and then I'll be checking whether my current window, which is like my L to R, okay, that is satisfying my question condition, which is max minus mean is less than equal to k or not. Okay, if it is, what I will do is I will simply increment dp of r equal to so plus equal to dp of L minus 1, right? So that's why we discussed right here. Okay, so the number of, so the count or the number of ways to partition the first L elements, okay, so that will be stored in my dp of L minus 1, right? Cool. So then I'll be doing a mod of that, because the question is saying that we need to do the mod. Okay, and let's say if I am keep on expanding and I arrive at an index, okay, where my condition is not meeting, so there is no benefit I will get if I go more backwards, right? So I can say whenever this condition stops meeting the condition, I will simply break out of the loop. Okay, cool. And finally I can return my dp of n. So basically the number of the total number of partition if I am considering the first n elements, right? So this is a valid solution. Okay, this thing is a valid solution, but the problem here is for every element, okay, I might be doing a complete uh, n element iteration. So you can think of like when I'm so there are like two for loops, right? And their ranges can vary between 0 to 1, 0 to n, okay? Which means I will get a overall time complexity of big O of n square, okay? And which is so if I look at the constraint, so this won't be like uh, this won't be getting accepted, okay, because my n is 5 times 10 to the power 4. So if n is 10 times 5 times at 10 to the power 4, so this will give rise to like 10 2.5 10 to the power 9. So I'll be doing like a billion number of operations, okay? So this will give me a happy TLE, so we don't want that, right? And by space complexity wise, this will be big O of n, which is acceptable, okay, because this dp array is what I'm taking, right? Cool. So how can we do something better? Okay, so let's try to think how can we optimize this for loop. Okay, so consider this case. Okay, if I do this, okay, consider this case where for this r, okay, I have multiple valid indices of L. Let's say this is L1, let's say this is L2, let's say this index is L3, okay. So all of these segments, okay, are satisfying my condition, okay. Now if you look, okay, if you look here, okay, I have L3 here, right? Now L3 here is smaller than L2, okay, and L2 is smaller than L1, okay, not equal to, smaller than L1, okay. So L3 is my smallest index, okay, which means the max and mean, okay, the maximum element between array of L3 to R, okay, that minus the minimum element between L3 to R, okay, that must be satisfying my question condition, right? Right. That means if I simply take the smallest index, okay, then whatever elements I'm having here, okay, whatever indices I'm having here, some let's say L4, let's say some L5, okay, those will automatically satisfy, right? Because the maximum element between L3 to R and the minimum element from L3 to R, okay, so their difference is already satisfying this, okay. So if I randomly pick, let's say if I am in this segment, let's say L2 to R, okay, so if I pick any element, those will be in bound with, so if I pick any element, so let's say some a of I, okay, so this a of I will be in bound with max of this guy, okay, R, and minimum of A3, L3 to R, right? And those elements will automatically satisfy my R, okay. So if I write it here, okay, so my dp of R, okay, that will become summation of the smallest index for which my L, so the smallest index or L, okay, that is satisfying my this condition, okay, to R, okay, that is basically that will basically give the answer of dp of r. Okay, so if I simply uh, take the smallest index, now whatever indices I'm taking from that L between R, okay, that will automatically give a contribution to my dp of R. Okay, so if I simply do a substitution here, so this will look like, okay, so if I want to write this in terms of L, okay, so this will look like dp of L minus 1 R minus 1 dp of L. Okay, cool. So this will look like dp of R equal to this. Oh, I have written a different notation, so basically this is dp of R and R. Cool. So now I have a relationship. Okay, now you can see this is nothing but the summation of all the dp's between L minus 1 to R minus 1, right? Now if I trivially try to do it, I'll be using a for loop and collecting all this sum, right, when I'm finding the answer for dp of R. Okay, but if I start storing my dp in a prefix way, okay, then I can get this value in constant time. Okay, so if I am having a prefix for my dp, okay, then my dp of R will look like prefix of, so R minus 1. This is the same way how we do prefix sum, right? So whenever we need to find the answer for like the summation of all elements between L to R, so we do dp of R minus prefix of R minus prefix of L minus 1. So similarly I'll be doing prefix of R minus 1 minus prefix of L minus 1 minus 1, okay, which is prefix of R minus 1 minus prefix of, oopsie, L minus 2. Cool. So this will be my dp of R. So this I can get in constant time. Okay, so this is the optimization over my dp calculation, because if I trivially try to find the summation of all the dp's that I have gotten from L minus 1 to R minus 1, okay, using a for loop, that will again give rise to a linear time complexity, right? Okay, so by doing a prefix some calculation over my dp's, I can easily get it in constant time. Okay, now the main question is, okay, how to find this L, okay, or the smallest index, okay, such that the segment from L to R is valid. Okay, how to find that? Okay, so for that so yeah, in order to find the smallest index of L, we can use a sliding window kind of approach. Okay, where for every index R I'm getting, okay, I can check, or so I can say something like this: I will initialize my window with some one element, okay, and I will keep on expanding, okay, which basically means I'll be incrementing my right index till my condition meets, or the uh, or the max of the window, which is L to R, minus mean of the current window, which is L to R, okay, satisfying this condition. Okay, I'll keep on expanding my R. Okay, but let's say I found a R, okay, which is not where my condition is not meeting. Okay, so for that, it means that I haven't found the perfect L for R. Okay, so that time I'll be shrinking my window. Okay, and in order to shrink, I'll be incrementing my L that time. Okay, So basically I will be keep on expanding using my R. Okay, so let's say I arrive at an index where my condition is not meeting, then I will be decrementing or incrementing my L, or decrementing the size of the window. Okay, so yeah, and so yeah, that's the idea. We'll be shrinking it. Now the thing is, how can we find the max and minimum elements? Okay, so for that we need to choose a optimal data structure to represent our window. Okay, so for that, okay, um, I will be using, for C++, I will be using map. Okay, why map? Because map is like a ordered dictionary in Python. Okay, where the first element always stores the smallest key that it contains, and the last element of map stores the largest key. Okay, and that automatically gives me the maximum and minimum element in my window. Okay, and yeah, as I am keep on shrinking my window, it may happen that my minimum elements are their count is like equal to 0. At that time I need to remove them from my window. So yeah, that's the idea. So yeah, from that I'll be getting optimal L's. Okay, for each index R. Okay, so it will look like something like this. So I think it's better if I code it up. Okay, then you guys will have a better clarity. But yeah, that's the idea. So once I find the optimal L for each R, okay, then I can easily do my DP calculation. Okay, using this. And in order to do the efficient DP calculation, like where I'm taking the summation of all elements from L minus 1 to R minus 1, I'll be using a prefix for my DP. Okay, and finally I'll be returning DP of N as my answer. So yeah, I'll be first coding it up in C++. So yeah, let's start. Cool. So first I'll be storing all the elements, the number of elements. Okay, so let's N for that. Then I need to do this modulus, and which means that integer might overflow when I am doing my addition in my DPs. Okay, so I will define long to capture my answer. Okay, then I'll be creating my DP array. So I'll say DP of n plus 1. I will initialize everything to 0, and similarly for prefix, which is for my DP, I'll be initializing with n plus 1. Okay, cool. Now as we discussed here, yeah, I'll be initializing my DP of 0 as 1. Okay, because if my whole array is a valid segment, then I need to take into account. Okay, cool. Then I'll be then initializing my prefix with DP of 0. Okay, like prefix of 0 should be DP of 0. Cool. Then I'll be using a map data structure in C++. Let's call it window. Okay, to represent my window. Okay, maybe we can stuck here. Yeah, okay, cool. Then I'll keep on incrementing. Now I will move my windows. Okay, so I'll initialize L equal to 1, R equal to 1. Now I'll be keep on iterating over this until R reaches N. Okay, and R plus plus. Okay, so first I'll add element in my window. So this will be nums of R minus 1 plus plus. Okay, then I'll check whether this window is satisfying my segment condition or not. Okay, so that I'll be doing something like this. Okay, so here I'll be doing shrinking. Okay, so while L is less than equal to R, and my windows maximum element, which I can get from R begin. Okay, first, which represents the key, minus window begin first. Okay, so this will give me the maximum element in my window, and this will give me the minimum element in my window. Okay, if the difference of these two is more than k, okay, that means I need to shrink my window. So I'll first remove the first element in my window, because yeah, I'll be shrinking by moving my left towards right. So I'll remove nums of L minus 1, decrementing the count. Okay, then I will be checking, okay, if the count of this element is completely gone, okay, or it has reached 0. Okay, then I need to remove this element from my finder, right? So I'll be doing finder dot erase finder dot find. I need to pass the pointer for this element nums of l minus 1. Okay, let's make it here. Cool. And then I'll be decreasing my window. I'll be by incrementing my l. Okay, cool. So after this while loop, I will arrive at a L, okay, that satisfy my current R. Okay, now once I find the smallest L for my R, okay, now I'll do my DP calculation, which is DP of R will become prefix of R minus 1 as per this, okay, prefix of R minus 1 minus uh, prefix of L minus 2. Okay, now it may happen, okay, L minus 2 becomes less than 0. Okay, so in order to solve that, I will initialize a left count. Okay, left count, and yeah, I forgot, like I need to use long here. Okay, and yeah, to satisfy modulus, and also I need to create my modulus ll mod 1 if 9 plus 7. Okay, oopsie, cool, ll this will be storing ints. Yep. Yeah, so this guy needs to be l, and I'll say if l is greater than equal to 2, then left count will become my prefix of l minus 2, otherwise it will be 0 only. So instead of using prefix of l minus 2, okay, I will use left count. Okay, cool, I'll subtracting it. Now since we are doing modulus, okay, so it's always a good idea to do a plus mod here. So whenever you are doing like subtraction, okay, and you need to find the modulus, okay, then only do it. Okay, for addition it's fine, and for multiplication it's also fine. Okay, but whenever you are doing a subtraction, so just keep a plus mod here. Okay, so that your values won't get negative. Okay, cool, then I'll be, so yeah, once I find this dp of r answer, then I'll be updating my prefix. So my prefix of r will become, so similarly the way we update our prefix, so r minus 1 plus dp of r, because this prefix is built for over my dp, right? So yeah, this is how I'll be updating my prefix. Cool, then finally I'll be returning dp of n. Okay, now I need to return end, and I can do a int here. Okay, now let's run it for all my test cases. Cool, we got error because I have written finder here, because I'm very fond of writing finder. Cool, so this needs to be window. Okay, I think we are good. Okay, and yeah, here also. So whenever this kind of counting happens, I always choose finder. So yeah, okay, cool, let's write this. Cool, all test case pass. Now I'm submitting, and yeah, we are good. Cool, so it got accepted. Now if I look at the time complexity, okay, so here also we are touching every element twice. Okay, but it's not like, so if I check the time complexity for this, so this guy will be moving all n iterations, right? So big O of n, okay, times, let's look at here. Okay, so here insertion might be happening, and maybe a searching of element and then incrementing. Okay, so this will be a log of big O of log of window size. Okay, then I have this while loop. Now in this while loop, I am touching every visited element again. Okay, but it's different than my two for loops what I was explaining here. Okay, because there it might happen for every element I am doing n iterations. Okay, but here using this two for loops, I'll be touching every element at max 1. Okay, so like at max 2. Okay, so for every element I will be touching them twice. Okay, cool. Now so this basically means this will become big O of 2n. Okay, now after this I'm simply doing a constant m operation. So yeah, this is my overall time complexity, which is big O of 2 times n, this is for my sliding window, times log of my window. Okay, because there are other logarithmic operations. For example, this here also we are decrementing the element count. Here also we are performing erase. Okay, so yeah, so those are all in logarithmic time complexity. So yeah, this will be my overall time complexity, which is basically same as this big O of n log n approach, because the maximum size of my window uh, can be n only, right, with n elements. Cool. Now as per space complexity, so at one instant of time the maximum number of element my window can carry is n, so that will become big O of n. Cool. So yeah, this is this code solution for C++. Now let's do it for Golang. Cool. So for Go, so there is no definite structure for map. Okay, there is no order dict in Go, so we have to use a third-party library. So I can use something like this. So there is a implementation of redblack tree in Golang, so I'll be using that. Okay, yeah, I can maybe use this, and I believe they also have a version 2. Okay, so yeah, I'll be creating alias here and I'll be doing this. So they have a stable version too, so you guys can check that out, so you guys can use that. So after that I'll be saying red black tree. Okay, cool. Then but yeah, this thing only gives you functionality, but whatever functionality you need in your code, you have to implement that. So yeah, for that I'll be implementing my order dict. So I'll be using finder now, or I can say window. Okay, let's create a window for it. Okay, now I will initialize a tree here. Okay, and this will be a pointer to my red black tree. Okay, cool. Then I'll create a constructor for my window. Okay, so new window, and this should return me a pointer to my window. Okay, so I can return a pointer to my window, and I will initialize this tree with arbitrary new width, and yeah, the keys and value should be int. Then I need to pass a comparator. So for comparator I can use an anonymous function, so I'll say a b int. Okay, now if a is less than b, I have to return -1. Okay, else if a is greater than b, I have to return 1, and if both of them are equal, I have to return 0. Yeah, cool. Now I'll use a comma here. Cool. Then two functionalities I'll be needing. Okay, that is like when I'm adding up element and increment their counting. Okay, so for that I'll be creating a function. So I'll be saying, let's call it handler. This will be my window. Okay, so pointed to my window, I will implement a add functionality which takes an integer. Okay, and it basically increases the count of that in my window. So I'll say count, and if this exists in my window, so I'll be doing h dot tree and get the value of val. So what's the count of it? Now if this key exists, okay, then that means I simply need to increment the count by 1. Okay, so add put val, and I will do count plus 1. Okay, and this will replace my current key value pair with this updated key value pair. Okay, so earlier this will be stored as like val and count. Now I'm simply now I'm inserting val and count plus 1, so this will replace the older count. Cool. Now otherwise, if if that key does not exist, if val doesn't exist in my window, so I will put it in my tree. Okay, and I will give a count of 1. Okay, cool. Now similarly I need another functionality, which is this erase functionality, right? So for that I will be implementing remove. Okay, so h window remove, it takes a integer, okay, and it doesn't return anything. So again I will check whether the element exists or not. Okay, so s3 get val, so this will give me the count of that and whether that key exists or not. If that key exists, okay, then first I will decrement the count. Okay, so I'll say if count minus 1 is equal to 0, then I need to remove the entire key value pair, which I will say tree remove val. Otherwise I'll simply update the count, which is h.tree put for this val I'll do count minus 1. Okay, cool. So yeah, I'll be doing this operation if my element exists in my tree. Cool, so that's for that. Then I can implement some functionality to get the maximum and minimum element in my window. Okay, so I can say handler window. So to get the mean element, I will implement this function and it returns an int. Okay, now in order to get the minimum element, so in this red black tree you can use their left and right functionalities. So this is something like this. So s.tree, so this represent my red black tree. So there I can simply call left function. Okay, so this will give me a pointer to the smallest element in the tree. Okay, so that I will, so first I will check if that is nil. Okay, if that is nil I can return 0 maybe. Okay, otherwise I'll return s.tree left, and I need the key, okay, not the value. So yeah, similarly I can copy this to implement max. Okay, I'll be using their right method over the tree, which gives us the maximum element. Okay, so yeah, I'll check for right and key. Cool, then I think I'm done with all my functionalities for the window. Now I'll write the same stuff that I have written in C++. Okay, so first I will take the length of my array, so len of nums. Okay, then I will create my DP array, so which will be make int, and this will be this will be of int 64, because yeah, if you remember I was using I can decrease this bit. Yeah, so yeah, I was using long here. Okay, so I will be using int 64 here. So I need a n+1 size array. Then I will say dp of this make int 64 n+1. Okay, so this will be for my prefix. Okay, cool. Now after that I'll be creating my window. So I'll say window, I'll be calling the constructor, which is new window. Okay, cool. Now after this I'll be now iterating over my array. Okay, and before that I need my mod also. So I'll say mod, I can say mod, it will be of type int64. Okay, and I will initialize it to 10 to the power 9 plus 7. Cool. Then yeah, also I need to initialize my dp as 1 and prefix of 0 as 1. Okay, then now I can iterate. Okay, so I'll say lr, I'll say 1 and 1, r less than equal to n, r plus plus. Now I will include that element, include my current rth element in my window. So I'll say window dot add nums of r minus 1. Okay, cool. Then I will check whether I need to shrink the window or not. So for that I will say while or like for l is less than r and now I can call my finder max function. So finder dot max minus finder dot mean. Okay, greater than k. That means I need to shrink my window. So I will first remove the first element from my window. So that will be remove nums of l minus 1 and l plus plus. Okay, cool. Now after that then I'll be updating my dp. So dp of r equal to prefix of r minus 1 minus yeah, here I need to do prefix of l minus 2, but prefix of l minus 2 might give me an error if l is like less than equal to 2, because that will be negative. So for that I'll be creating a left count. So I'll be initializing left count int 64. So first this will be 0. Then if only l is more than 2, then my left count will become prefix of l minus 2. Okay, and this I'll be using it here. And for a safe modulus, I'll be doing a plus mod here, and I'll be doing the overall modulus here. And then for prefix of r, I'll be updating my answer with prefix of r minus 1 plus dp of r. Okay, cool. And then finally I'll be returning int of dp of n, because dp is a int 64 array, so I'll be returning int of this. So let's run this. Cool, taking time. Okay, it threw an error. Is it not the package rbt this? Okay, let's search. Redblack tree in Golang. Package. Trees got this. Let me check whether this is correct. Take some time, just a second. Cool. So yeah, an S was missing here. So yeah, so after this, when I ran it, so it's saying finder. Oh, I'm very fond of finders. Okay, so this will be window, and this will be window. So window of this, and here also window. Cool. Let's run this. Cool. All test case passed. Now let's submit. Cool, it passed. So the time complexity is same what we have written for C++. So redblack tree also do the insertion and removal in log and time complexity. Okay, like log of their size. Cool. Now finally, let's do it for Rust. So yeah, so in order to do Rust, I'll be using BTree. So I'll be using collections, std collections, and I'll be using BTreeMap. Yeah, just a second. Yep. Cool. Then same what we did. So I'll be storing the len of the nums. Cool. Then I'll be creating my dp. Let mat dp. So this will be of vector of int64 type. Okay. Like which is like analogous to long in C++. So here I'll be creating vec of all element initialized to 0 of size n+1. Cool. Then similarly I'll be doing this for my prefix also. So I'll be saying prefix. Okay, and here I will update my dp of 0 to dp of 1, and same as prefix of 0 to dp of 0, or basically 1. Okay, then I'll be storing my modulus also. So mod, so this will be also of type int64, and this will be 0, 0, 0, 0, 0, 0, 0, 7. Okay, 10 is power 9, 10 is power 9 plus 7. I don't need this. Okay, cool. Then here I'll be using I need my L index, so I'll be creating an L. Okay, and now I'll be yeah, I also need my window now, so this will be window, and yeah, and this will be mutable, so window of BTreeMap, and I'll be calling the constructor. Cool. And with this I think I'm good to go. Now I'll be iterating over all by element, so that will be rn 1 to n. Okay, now first I will increment the count of my currently visited element, which is like I'll do finder of get the key. Okay, that is nums of r-1. Okay, if it is not present, then insert the value, so insert the key value pair with the value as 0, and if it is present, simply increment the count by 1. Cool. Then I'll be using a for loop, while loop to apply the string case logic while L is less than equal to R, and my finder is not empty. Okay, so this will be a little bit of different, because in Rust, so they don't directly give you the mean like minimum and maximum element. Instead they return you options. Okay, now in order to resolve those options, you need to write some extra code. So yeah, this is for that. So I'll simply check if finder is empty or not, and here I will have my condition check, which is like the max minus mean should be less than equal to k. Okay, so I'll collect the minimum element. I'll take the reference of that mean, and I don't need the count, so I'll say finder dot first key value. So it is the method. So this is the method that gives you the first key value pair in your window. And yeah, again I did that. So again, finder. This will be window. Cool. So finder, and I'll be unwrapping the option. So this will give me some value. Okay. Otherwise it will run. Otherwise it will give me a none value. So that is fine. I don't think I will get none values. Okay, and my Rust won't panic. Cool. Then I'll be collecting the maximum value. Yeah, let's call it maximum value, and this will be window of last key value. Okay, and I will be unwrapping that option. Cool. And now I'll have my condition check, which is max of v minus mean of v. If let's say if it is less than equal to k. Okay, so that means I have found my L. Okay, and I will simply break out of this while loop. So I'll say break. Okay, otherwise, okay, so I need to shrink my window. So here I will say if let sum. Okay, so I'll collect the pointer to my key value pair. Okay, so finder of window dot get the mutable reference for the for this key, which is nums of L minus 1. Okay, so for this key, give me a mutable reference for its value. Okay, because I'll be decrementing the count, right? So yeah, so count will be a pointer to the value, so I'll dereference it and I will decrement the count. Then I will check whether the count has reached 0. If it has reached 0, then that means I need to remove this key value pair. So I'll do window dot remove. I'll take this reference to the key, which is L minus 1. Okay, cool. Then here after that I'll simply perform this shrinkage, which is L plus 1 equal L plus equal to 1. Okay, so I'm moving my window from the left side. Cool. Then after this while loop, which basically means now I have found a L. Okay, for which my R is so I have found a L for which the nums of L to R is a valid segment. Okay, so for that I'll be updating my DP. So this will be prefix of R minus 1 minus here also I'll be using the left count logic and plus mod and mod. Yeah, I keep it like this, right? Mod. Then I'll be creating a left count here. So the same code that we have written for C++ as well as Golang, so that I'll be writing it here. So left count equal to 0. Then if left count is greater than equal to here I will check if L is greater than equal to 2, then I will update my left count to prefix of L minus 2. Cool. Now this will update my DP. Now in order to update the prefix of my DP, so I'll do prefix of R minus 1 plus DP of R. Cool. And finally I'll be returning DP of N. Now DP is initialized at as I64, so but the question expects we should return I32, so I'll be doing DP of N as I32. Now if I run this, hopefully it should work. Okay, I forgot a modulus here. Okay, initial test is passed, but yeah, here I need to do a modulus. So mod. Cool. Now let's submit. Cool, it got accepted. So yeah, the time complexity is same because the B tree is very similar to the map you have in C++, and it's similar to the redblack tree implementation that I showed you in Golang. So yeah, all three languages done. So yeah, that's the idea. So let's just do a recap. So we started with the partition. Okay, so there we observed that we will have a exponential time complexity if we go via if we go via brute force, where we partition it, and for every segment in that partition we check this condition, so that will give you a TLE. Okay, like that will give you exponential time complexity. Then we searched for then we thought of this process where we will fix an r, okay, and then for r we observed a pattern for whatever else we have, okay, that is satisfying my segment, or like that is setting that is satisfying my question condition, like array of L to R uh, should satisfy this condition, okay. From that we build an analogy like, okay, so for this L, okay, if I know the number of ways in which I can perform the partition for the first L elements, then all that count will be taking this array, right, uh, when I am computing the answer for R, okay. So from that we got this analogy, okay. So for every valid index L, so I'll need the count of answer of L minus 1. So this looks like a very DP solution, okay. Then we thought of this DP, okay. Then we defined our DP state, which is like the number of ways to correctly partition my first R elements, okay. Then yeah, from that we went through a, not a naive but a DP implementation kind of a solution, but here we stuck at like we were doing a quadratic time complexity in this algorithm, okay. Then we went through how we can optimize this. Now in that optimization approach we look for we had this observation where we don't need every L. Once we find the smallest L for which my R is satisfying, so basically like my L my array of L to R is satisfying, then whatever indices are present between L to R, okay, those will automatically give a valid partition, right. So yeah, from that we came to realize like this should be my DP condition, okay. Now here we saw that, okay, we can do one more optimization, which is a prefix over my DP, okay. From that I can get this summation in constant time, so we build a prefix over my DP analogy. Now the question now the next problem was like how to find the smallest index for R, and for that we went through this sliding window, and all the implementation of this sliding window I have shown you in this code in 3 languages: C++, Golang, and Rust. So yeah, that was all. So if you learn something new, please do like and subscribe to the channel, and if you have any doubts you can post in the comment. I will be happy to answer all your questions. So yeah, just stay tuned to watch more videos. Bye bye.